Okay, so we're going to start off with the concept of a binary operation. So definition, a binary operation, and then this symbol, I'll pronounce it O plus on the integers, is a function that assigns to each ordered pair of integers a unique integer denoted A, O plus B. Now I use that type of symbol O plus so that it's very generic. It could represent any standard operation. So it might be just ordinary addition, or it could represent subtraction or multiplication, and so on. So it's just a general symbol for any type of binary operation. So let's start by considering the addition operation. Now, in the definition, I have the word function. So when you study calculus, what were functions? Functions were rules that assign to each element of a domain a unique element in the range. That same concept we're using right here. So think of this as being the domain. And over here we have the range. And so we have in the domain ordered pairs like 2 and 3. Okay, these are ordered pairs of integers over in the domain. And then there, we have a function and the function is just add the two numbers together. That's a binary operation. So I take the ordered pair 2 and 3, I add them together, and I get an integer in the range. So if I take negative 3, 5, I add it together, and I get 2. So the concept of a function is one. For each ordered pair, there's a unique output. So give me a pair, the sum is a uniquely defined number. That's what a binary operation is. Subtraction and multiplication are also binary operations. If I give you subtract two integers, I get a unique, well-defined integer, negative 3. So if I multiply two integers, I get a unique, well-defined integer. So these are other examples of binary operations. How about this next example? Is division a binary operation on the integer? So I see people shaking their heads. Well, if I go 6 divided by 2, that's an integer, or 18 divided by 6, that's an integer. That it worked out that time. Why were you shaking your head? Yeah, if you did it the opposite way, you can get all sorts of examples where division of two integers, the output is a rational number, but it's not an integer. So this is 2, 6. So if you put a line through, that means it's not an element of the integers. So the answer here is no. You just need one failure to say it's not a binary operation. Doesn't matter how many successes you have. Single failure, that's all you need. All right, let's create a new binary operation. I'm going to define A, O plus B to be 2a minus 3b. Non-standard binary operation. But why it is that it's a binary operation? If I give you two integers, you got to hear me here. Two integers, a and b, and I plug them into that formula, is the output a uniquely defined integer? What's the answer? Yeah. 2 times a minus 3 times b. There's no ambiguity. You're going to get a unique, well-defined integer. So, for example, 3, O plus 5 means what? Well, you got to be careful. Which number do I multiply by 2? And which one by 3? So the order of the operation is critical when you define a binary operation. It's the first number that you multiply by 2, and the second number by 3. So this would be 2 times 3 minus 3 times the second number. So 6 minus 15, that's the opposite of 15 minus 6, which is 9, to negative 9. If I switch the order, 2 times the first minus 3 times the second is 10, which is 1. Both times I get a unique integer. What did you discover about this example, though? Compare those two numbers, they're different. So this is completely different than ordinary addition, where the order does not matter. Which one we have first, which one we have second. This is what we call a non-commutative operation. A O plus B is not equal B O plus A in general. You can probably find examples where it works, but again, one example is all it takes to say this is not commutative. And I've jumped the gun. We haven't defined this word, but I think you've seen these concepts. So this is the definition of commutative. A binary operation is called commutative if AO plus B is the same as BO plus A for all choices of A and B. If there's a single failure, it's not commutative. And of course, built into the axioms for the integers, and we'll write those down in a while, are the facts that ordinary addition and multiplication are commutative operations. We're not going to try to prove those things. We just take those as axioms for the integers. So A plus B is always equal to B plus A. And generally, when you introduce this concept, if you're an educator, you draw a little model to kind of convince someone that this is true, and you might use like sticks. So you put a stick of length A next to a stick of length B. A plus B is the total here. And if you switch the order, you're certainly going to get the same length. It's the same two sticks. You switch the order, and you're getting B plus A. So it's kind of a self-explanatory. And A times B and B times A. Does anybody know a nice geometric model why A times B is the same as B times A, especially if you're in secondary ed? One of the standard models. You draw like a yeah. A rectangle. A rectangle, yeah. So if you take, let's do 3 times 5, for instance. So how many little squares do we see here? I've got 3 rows, each with 5 squares, 3 times 5. That adds up to 15. But you don't, the word 15 is a distraction. This is 3 times 5. So 3 rows of 5 each. And if you just rotate it, you got 5 rows with 3 each. But certainly you have the same number of squares in both of these rectangles. So you got 5 by 3. And so 3 times 5 is the same as 5, 3. 3 5 equals 5, 3. And again, if you go back to scratch, it takes a fair amount of work to prove statements like this from real elementary axioms for the whole number. We're not going to do that. We just take these as given axioms and then go from there so we can make some progress this semester. How about subtraction? Is that a commutative operation? No. A minus B. And just give one example to show something fails. Not equal. All right, now you've all had a lot of math at this point, probably up to Calc 3 even. Can you think of other non-commutative binary operations? Doesn't have to deal with integers that you've encountered, besides subtraction. It's real standard operation where if you switch the order, you get a different outcome. And I'm thinking of 3 examples. One is in basic algebra up through college algebra. You would have seen lots of examples. Another one is in Calc 3. And another one if you've had matrix theory. Anybody had matrix theory yet? All right, let's see if we can pick out what 3 examples am I thinking of. In Calc 3, you're saying? Yeah, the cross product of 2 vectors, right? These are vectors in 3-dimensional space. When you take the cross product, the order matters. You have that right-hand rule. You either go this way or you go that way. So that's a non-commutative operation. Matrix theory. Some of you said you've had matrix theory. Which is the non-commutative operation? We'll do a little matrix theory this semester. Multiplying, yeah. A times B. When you multiply matrices, it's not commutative. AB doesn't equal BA. And how about in just college algebra or high school algebra? The binary operation. I think I have a more general operation. We combine 2 functions. Okay, that's another interesting one. Exponentiation. A raised to the power is different than B raised to the power. We're not going to do here. So you got, yeah, A to the B. The one I was thinking of is function composition. If you take 2 functions and you combine them together by composition, the little O symbol, then order is very important. So F circle G is different than G circle F. So there's lots of examples of non-commutative operations. The next the concept I want to talk about is the associative law. So the associative law comes into play if you want to add three or more objects together, and you have to come up with some rule for how do you go about adding three or more objects together. So suppose I go 2 plus 4 plus 7. I could do it from left to right, or add the 2 and the 4 together. So remember, binary means you can only add two things at once. I'm trying to talk about the general concept for a binary operation. And then add 7. That gives me 13. Or I could add the second two numbers first, and then add the first one. Two plus 11. Now, it looks at this point like it's completely different what we're doing. 6 plus 7 as opposed to 2 plus 11. But of course, in the end, it comes out to be the same. And that's what we call the associative law. But it doesn't matter which two numbers you add first, you're going to get the same outcome. So this is the general definition then. A binary operation, O plus, is called associative if A plus the quantity B plus C is the same as A plus B plus C. So it doesn't matter whether you add the first two things first or the second two things first. You always get the same outcome. And that is so essential. We just take that for granted when we're adding or multiplying lists of numbers. We never worry about the grouping, which do we do first. There's a whole branch of mathematics called non-associative algebra, where that rule breaks down. And it's really nasty to work with calculations in non-associative algebra. I've never dealt with that branch myself. This semester, everything we do will have the associative law, so you don't have to think so carefully about the order in which to do things. So for instance, ordinary addition and multiplication are associative. And generally, when I write a statement like that, I haven't written a complete thought because I haven't told you what A, B, and C are. So if I want to squeeze something right in here, right? I do that for all integers A, B, and C, just to abbreviate. Yeah. I'm not sure. Only this first week when I'm actually trying to do things real systematic. Yeah, this first week will be a little more detail oriented, and then after that, we just want to get on with things. But I want you to get really familiar with all these axioms right now. And the same thing for multiplication. Then you combine these two operations, and we get what I call the general associative commutative law. So no matter how many numbers you're adding together, you can regroup them and add them in any order you like. And so we're going to freely use that principle after this first week and not worry about every step having to group parentheses. So in this example, I could go from left to right, and I'd have to work a little bit. 37 plus 19. Well, I don't want to have to carry the numbers and do that in my head. Who can see an answer to that really quick? Yeah, I'm just talking about what's a real easy way to do this just by doing it in the right order. Yeah. Yeah, just if you put together the 37 and the 13 and the 19 and the 31, that's what I mean. You're free to do things any order. I've switched the order, I've regrouped. There's lots of steps of associative and commutative laws going on there. So we just do that all at once. And you get 100 coming out. And the same would work for multiplication. You're free to multiply a list of numbers any order you like, and you'll always get a unique outcome. All right, next I want to talk about the concept of an identity element for a binary operation. So an element E is called an identity element for the binary operation plus. It's A plus E equals A, and E plus A equals A. So adding E onto that binary operation doesn't change the object you're adding it to. That's what we mean by an identity element. And it has to work in both directions. And the reason we put both directions is for a non-commutative operation. It's critical that you test it from the left side and the right side. Sometimes it'll work from one side, but not from the other side. So the standard example, 0 is the identity element for ordinary addition, because A plus 0 is A, and 0 plus A is A for any integer. 1 is the identity element for ordinary multiplication. A times 1 is A, 1 times A is A for all integers. All right, so I'm creating a new binary operation in the third example. I wonder what that beep beep sound is coming from. I haven't figured that out. So this new operation, A plus B, is going to be A minus 3 times B. And you notice the little colon I put here? So if you see this colon, that means I'm defining a new operation. So that's just signaling to the reader, this is a definition. So if you see the colon equals, that means I'm defining this operation to be A minus 3B. Is there an identity element? So I'd say, well, let's suppose E is an identity and solve for E. Then go back to the definition. So that means A plus E should equal A. And just write down, what does that mean? If A plus E equals A, then A plus E is A minus 3B. In this case, B is E. So A minus 3E should equal A, and that should be true for all integers. And I'm trying to find out what value of E makes this work. So A minus 3E is A for all integers. What's that going to imply B equals? Yeah, just solve for E. And for these problems, just use counts. Don't worry about all the rules going on. Just these ordinary techniques, cancel A from both sides. And 3 times E equals 0, so E equals 0. Do you think 0 is going to work as an identity element? That's all for E, it has to be 0. Is it going to work? Well, we have to test the other direction. So now we have to test E plus A equals A. If 0 is identity, that's the only possible identity. Then the second rule says E plus A equals A. Well, again, this is 0 plus A equals A. Definition of 0 plus A is 0 minus 3A so is that going to be true? Because 0 minus 3A always going to equal A. And obviously not. Minus 3 times A is not going to be A in general. It's a false statement. So although 0 works from one direction, it fails from the other direction. So there's no identity that's going to work. 0 is the only possible value, but even it fails from the other direction. No identity. And then the final concept is this idea of a set being closed under a binary operation. So let's suppose S is a subset of integers. Then we'll say the set S is closed under the binary operation plus if for any A and B in S, A plus B is always back in X. So that was built into the concept of a binary operation on integers. The sum of two integers is an integer. But here I'm taking a subset of integers and asking, is that set going to be closed in the given binary operation? Let's go to our standard sets to look at examples. This is something that this concept we have to get at in grade school that you may not have introduced a formal definition. Set being closed under an operation. So is a set of even integers closed under addition? So what am I asking? If I take two even integers, add them together, do I get back an even integer? An even plus an even, and even. And that's something, we'll prove things like this next week, but right now I'm just taking it to see if you know this concept. So yes, sum of two evens. Even is the set closed under multiplication. If you take a product of two even numbers, 2 times 6, 8 times 4, yes, product of two evens. Even subtraction, you subtract two even numbers, you get an even number. How about the odd integer? If you add two odd integers, do you get an odd integer? The answer is no. 3 plus 5 is 8. So that's an example of a set not closed under a binary operation. So. Multiplication. Product of two odds, 3 times 5, an odd times an odd is an odd. Yeah. And then finally, subtraction. You subtract two odd numbers. That's kind of like adding two odd numbers. And the answer is no.